Good afternoon, everybody. Welcome back. We're looking today at lesson 31.02, which deals with what we call optimization problems, also known as applied maxima and minima problems. And this is just part A of the lesson. You can find this on page 7 of your lesson handout. We're going to be spending 3 different lessons learning how to do optimization problems. When you optimize something, you make it either as large as possible or as small as possible, depending on your needs. So I'm just going to give you a couple of quick illustrations here. The first one is something where you're trying to minimize something, and you're trying to minimize the cost of materials to make a can. So I'd like you to imagine that you're the owner of a new soup can company, and you're designing soup cans that are going to be holding 1 liter of the product. That 1 liter being the volume is what we're going to talk about later on as being called a constraint. No matter how you design the soup can, it has to hold 1 liter. I've got 3 different soup can designs up here. The design on the left has a very, very small radius. The radius of this can is quite tiny. And as a result of that, if you want the can to hold 1 liter with such a tiny radius, you need a very, very tall can. On the other hand, this can on the bottom has a huge radius, and if you want to use that radius for the can to hold 1 liter, then you don't need the can to be as tall. It can be quite short. And then the can that I'm indicating now has a kind of middle of the road radius. And even though these 3 cans have 3 different radii, the fact of the matter is they all hold 1 liter of the product. And that 1 liter is referred to as the constraint. And if you were to think about the can that's very tall and the can that's very short, they're both very wasteful because they're going to cost a lot of money because of the amount of material you need to build the can. The surface area of those cans is going to be larger than the surface area of the can that has the medium radius. And as a result, you have this graph which shows the behavior of the radius of the can and how it influences the surface area of the can. At very, very small radii, the surface area of the can is quite large, and at large radii, the surface area is quite large. But there's this point in between where things are just right for our purposes. If you can identify the coordinates of that point, then not only will you know the radius that produces the most economical can, but you'll also be able to calculate what the surface area is. And it shouldn't be lost on you that that point corresponds to a minimum value of a function. So to determine the coordinates, it's simply a matter of coming up with the formula relating y and x so that you could find dy dx and do what we've been doing for the past 2 days, which is to do a first derivative of the function so we could find the critical points so we can identify maxima or minima. Here's a different situation. This is one that you have encountered in Math 20. There is a typing mistake on your handout, though, that I've highlighted. The graph should have for x decrease in ticket price, and I believe in the handout it said increase in ticket price. So if we go through this, it says a concert promoter recognizes that when she's charging the current ticket price, she gets a certain amount of revenue. And if she were to try to attract more people, she could start decreasing the ticket price. So what happens is as the ticket price initially starts decreasing in value, the number of people who buy tickets goes up. And even though they're paying less each, the total revenue starts to climb. But what's going to happen at a certain point is the amount of the decrease in the ticket price will be so large that the price per ticket will really be tiny. And even though she might attract a huge, huge number of people to this concert, since they're not paying very much each, the revenue falls off. So again, there's some kind of optimal point here where if you could determine the coordinates of this point, you could determine how much the ticket price should be decreased by for her to get the most possible revenue. And this is a problem in Math 20 you did by finding a quadratic function and then completing the square to determine the coordinates of the vertex. Well, we're going to see that if you can come up with the function, it's much easier to determine the coordinates of the vertex by differentiating. What is important in all of these problems is that you come up with a function where the variable that you want to be as large or as small as possible is f of x. It's the y coordinate. And you define that y coordinate in terms of some other variable, which is the independent variable. So I want to go back and just talk briefly here about the soup can problem. When you take a look at these three soup cans, not only do they have different radii, they have different heights. And when you look at the graph of the function has surface area as a function of radius, which means the relationship has to be between surface area and only radius. You cannot have a height in the equation, because if you have a height in the equation, you can't talk about d surface area, d radius of can, because there will be a third variable there. So let's keep that in mind when we take a look at these examples. The first example says find two positive numbers whose product is 80. And I want to stop right there and define the two numbers as being A. A is the first number. I would stay away from using variables of x and y, to be perfectly honest. And B is the second number. And you're told that the product of these numbers is 80. So AB equals 80. And this is a very important relationship here. In this question, this is what's called the equation of constraint. To constrain something means to confine it to a certain condition. For example, when I talked about the soup can problem, the constraint was you had to have 1 liter. Here, the constraint is that the product of the two numbers has to be 80. Now, what we're also going to do is identify, or I guess, pick a variable that we can use for the thing we want to be optimized. And since you want the sum of these to be optimized, I'm just going to choose S as being the sum. And I'm going to put in brackets to be minimized. So that means the sum is equal to A plus B, and A plus B is to be minimized. But now we have a problem. See, we want sum to be a function of only one variable. And I'm going to choose that variable. I'm going to say, let's use A. You cannot have the sum defined in terms of more than one variable, otherwise it doesn't make sense to find dA ds in this example, because then you're also going to have, let me back up, I misspoke there. It doesn't make sense to have this equation S equals A plus B, because then when you want to find ds dA, you're going to end up with dB dA in there as well, and you can't start to imagine a graph showing the relation between S and A. Sorry for my misstatement a minute ago. So we need to get rid of one of these variables, and that is what the equation of constraint is used for. The equation of constraint is typically used to eliminate one of the variables. So if we take that equation and we rearrange it for B, we get 80 over A, and we can put that in for B in our function. And that gives us S equals A plus 80 over A. And that is the function that this graph is in reference to. We want to differentiate that to find out where the minimum is. Before we differentiate it, I would recommend, of course, writing it as A plus 80, A to the negative 1. And now we're ready to differentiate. This is not like related rates. We're not differentiating with respect to time. We're differentiating with respect to the independent variable. So the derivative of A is 1 with respect to A, plus the derivative of 80A to the negative 1 is negative 80A a to the negative 2. And we do what we've been taught to do and what we have been doing the past couple of days. You factor completely. And that means ds dA equals, I can factor an a to the negative 2 out and be left with a squared minus 80. And that tells us the derivative ds dA is equal to a squared minus 80 over a squared, which gives us the following critical values for a. One of the critical values of a is 0 because it makes the derivative undefined. One of the critical values is a equals positive root 80, and the other is a equals negative root 80. Now, to set your mind at ease here, until we get to more complicated max-min problems, you should not have to do a first derivative chart. You should be able to eliminate all but one of those critical values because they are not in the domain of allowable values of a. First of all, remember, the product of the two numbers must be 80. Well, that tells us that the first number, a, cannot be 0. We can knock that one out because if a is 0, then the product, there's no way it can be 80. B would have to be undefined. The other thing is in the question, you are told that they are two positive numbers, which means that the value of a that produces the minimum sum cannot be negative root 80. So we don't need a first derivative chart here. We've determined that the value of a is the square root of 80. And now we can use our statement that b was equal to 80 over a to find out the value of b. B will be equal to 80 divided by root 80. And I won't bore you with the details, but if you rationalize the denominator, you will get root 80. So the answer to the question is the two numbers that multiply to give 80, and there's an infinite number of pairs of numbers that multiply to give 80. But the one pair that has a sum that's as small as possible is this pair of numbers, root 80 and root 80. 8 times 10 gives you 80, but 8 plus 10 is 18, which will be more than root 80 plus root 80. All right, let's take a look at the next question. This is a classic problem in max-min problems. We're dealing with a farmer, and this is a very contrived situation. He or she wants to make a rectangular pen, and he is going to house his snakes, poodles, and pit bulls. And he's going to be a little bit crafty about it by using 600 feet of fencing, but he's going to use the side of his barn in order to build the pen. And here's one of his designs. What we've got over here is the barn. And then we have all this fencing. And I'm just going to choose to highlight the fencing for you. You really don't need to highlight anything on your paper, but I just want to put up here that these yellow lines that I'm highlighting are the 600 meters of fencing. So there's a lot that we need to work out here. However, let's start off with the fact that area is to be maximized. Well, how are we going to define area? I guess what we're going to have to do is say area is length times width. Because this rectangle, forget about the yellow lines for a second, look at the bluish colored lines. This rectangle has an area defined by the length multiplied by the width. Right? If I call this the length and this the width, then that's how we would find the area. But the problem is area equals length times width is no good. We want only one variable. This is a difference between max-min problems and related rates. With related rates, you can have as many variables as you have rates of change. Here, we want to imagine that we are going to be constructing a graph. We never really look at the graph, where area is a function of one of these variables. I'm going to pick W, but you can choose whatever variable you want. So we need to get rid of, if we choose W, we need to get rid of L. And to do that, we're going to use an equation of constraint. I'm going to pull off of here the blue rectangle because I think it might confuse you in the next step. When we take a look at the yellow pieces, which are the pieces of the fence, each of these 4 pieces is a width. And that means that that one length plus those 4 widths has to give you, I believe it was 600 feet. And this is our equation of constraint. Now I happen to be kind of looking ahead, and I chose to keep W because it's going to be easier to rearrange this top equation for L. But regardless, this is our equation of constraint. Am I going to fit it in there? Barely. That is our equation of constraint. So if I rearrange that for L, what I'm going to get is L. I'm going to get L is equal to 600 minus 4W, and I can load that 600 minus 4W into my area equation and get area equals 600 minus 4W multiplied by W. And now again, I have an equation that the graph, and we're not really going to draw the graph, I'm just saying we need to visualize that there is some graph. That graph is now connected to a function where A is a function of W and nothing else. You're going to have to differentiate it to find the critical values of W, but before you differentiate, we have learned this from the beginning of the course. Well, from the point we started differentiating, I've tried to stress to you that you want to get things in a form that makes differentiation easy. And if you were to differentiate the function from here, then that would require the use of the product rule. And I don't think you want to do that. Maybe you do, I don't know. I wouldn't want to do that. I would prefer just to go with the simplified form, which is A equals 600W minus 4W squared. To differentiate that, well, there should be absolutely zero question as to how to do it, and the amount of thought that goes into it should be quite limited. dA dW equals 600 minus 8W. By the way, I don't know if you noticed this, I tend to pick for my dependent variable a capital letter. I don't know why I do that or where I picked that up. The nice thing about this, by the way, this is a Math 20 problem that you would be able to do last year, but look what you would do in Math 20. You would do a completion of the square. And probably if I were to ask you, if I had you as a class in front of me, how many of you would like to complete the square? I don't know of too many people that would put their hand up. And probably if I asked you, how many of you remember how to complete the square? I don't know. I think most people kind of forget. It's quite a complicated, tiresome process. So we did learn how to solve these problems last year, but look how easy it becomes now. dA dW equals, now does 8 go into 600? Well, I mean, it does divide into 600. I mean, can we factor an 8 out without remainder? I think it's 75. I'm just going to take 8 out. And write 75 minus W, and then I'm going to double check here. Mike, calculator is not displaying on the screen for some reason. I have to fix that, so I just want to double check. 8 times 75 on my calculator is in fact 600. And that means, everybody, that the only critical value of W is 75. It's the value that makes the derivative 0. So there's no need for a first derivative chart. You have to trust me that this will correspond to a maximum area. So what are the dimensions? They will be 75 wide. And now we have to work out what the length is. But that's pretty easy. All we have to do is put 75 in for W in our expression for L. So if I take 4 times 75, I get 300, which means that 600 minus 300 is 300. The answer to the question is he will get the maximum area possible if he designs it as being 75 by 300. And again, this is actually a Math 20 problem, but we solved it with calculus. Now the question, part B, is what if he designs it this way? Now this is a little bit different. Here we have an L, an L, an L, a W, and a W. The W is all the way across, which means that this time the equation of constraint is 3L plus 2W equals 600. Well, our area is length times width. Now you have to decide which variable to get rid of. And I'm not really sure that it matters. If you rearrange this equation of constraint for L, you're going to get L equals negative 2/3 W plus 200. So you're going to be getting a fraction. So what I did there is I moved the 2W to the other side where it becomes negative, and I divided everything by 3. If you choose to rearrange for W, then you're going to end up with W equals negative 3/2 L plus 300. So what I've done there, and I'm just going to double check that, is I've moved the 3L to the other side and then divided everything by 2. So it doesn't really matter. I'm going to stick with rearranging for L to eliminate L. My equation then becomes the length, which is negative 2/3 W plus 200 times the width. I'm pretty much ready to go, but before I differentiate, I'm going to multiply that W through to get negative 2/3 W squared plus 200W. Then I can differentiate everything with respect to W. Again, with max-min problems, you're always going to differentiate with respect to the independent variable. And I get negative 4/3 W plus 200. I wouldn't worry about factoring here or trying to do anything fancy. Since your derivative is linear, we can just go ahead and set it equal to 0 and solve for W. So if I set this derivative equal to 0, I get negative 4/3 W plus 200. I can multiply both sides by 3 and get 0 equals negative 4W plus 600. So what I'm doing here is I'm multiplying the left side of the equation by 3, and I'm multiplying the right side of the equation by 3. I can move the 4W over and get 4W equals 600. And that means W is equal to 600 over 4, which I'm pretty sure is 150. I don't know why I'm bothering to check on a calculator, but sometimes my mind slips a gear and I can't do that in my head. It is in fact 150. So this is the only critical value of W, which means it must be the answer to the question. Go back up to the top here for you. That means that we have 150 for the width. And now if we want to know the length, I guess what we could do is we could use this formula. We could put 150 in for W, take negative 2/3 of that 150 and add 200. I mean, the other thing you could do is just take 600 and subtract the 2 widths of 150 each. I think what you're going to get is 100. Yes, you're going to get 100. So now let's review stuff here. We're done. If the farmer decides to construct the pens using this design in part A, it will be 300 by 75 will be the dimensions of the pen. If he decides to do it this way, it will be 150 times 100. And part C says, what's the better design? Now the word better here implies more area. The farmer wants his animals to be happy. He doesn't want them crowded into small spaces. The whole purpose of having a pen and animals is for the animals to move around and get exercise, among other things. So which is a better design? Well, in A, the area is, I'm going to have to go back and look at this, I'm sorry, 75 by 300. I want to say that's 225 followed by 2 zeros, but I better check it on my calculator. Yep, 22,500. I'm pretty sure it was in feet, so this would be square feet. In B, the area would be the 75 by the 150 by the 100. Yep, 150 feet multiplied by 100 feet, which gives 15,000 square feet. So the design that's the better design, the optimal design, would be this one, because you get more area. And if you were in post-secondary, what you might be told in a problem like this is just that the farmer is going to use one side of the barn and construct a rectangular series of pens. What's the maximum area? And you would have to recognize that you could try this design and then you could try this design and compare them. That's a possibility in post-secondary. I hope you're able to follow that. Pretty basic questions. In fact, all of the examples we looked at today end up being basically quadratic in some way. The first one is not exactly quadratic, but it turns into a quadratic if you neglect the denominator of the derivative. So there's nothing very complicated here. The problems that I would like you to try for next time are on page 188, number 1 and 2. Number 7, just do part A, and then number 8. And as we progress through these lessons, things will get, well, progressively more difficult. So I hope you have a great rest of the day, and we will talk to you soon.